All right. So, hello everyone. Good morning and good afternoon, good evening, good night if somebody else is following this webinar at nighttime. And my name is Francesco Marra. I work at the University of Salerno. I'm going to talk about the benefits of virtualization in food industry in this series of webinars dedicated to the cost action 15118 FoodMC. So, very shortly, I want to tell you a little bit about the agenda. So, we'll spend some words about why virtualization is important in process industry and what is the status of the food world in terms of innovation and usage of tools for innovation. What are the benefits of computational activities and virtualization? And then if we can give a little bit of definition about what is modeling, what is simulation in this field, we'll spend also some words sharing some peculiar news about modeling and simulation, talking about the essential steps, and finally about what virtualization, modeling, simulation will be in the future of the food industry. Okay, so if you talk with an IT or computing specialist, he will have a very clear concept of what virtualization is. But in the process industry domain, the meaning of this concept can be seen slightly different, and we could define with virtualization a list of activities that could be purely intellectual and or mathematical computational, such as data modeling, statistical analysis, fundamental modeling, dynamic simulation and optimization, but also computer-aided design and engineering that can be included in a unique, wider scheme, larger umbrella called virtualization of process. Virtualization is not detached from reality. It is into reality because any phenomenon to be modeled in a mathematical way, in a mathematical formulation and solved needs a deep observation and knowledge of the reality. So the interpretation of results lead to the virtual tool, and any virtual tool need validation. In other words, to be effective, any virtual tool has to be trustable. Okay, so why it's important to have computation activities in the industry? Because using virtual tools, it's possible to reduce the overall time needed for developing, designing, and validating processes and equipments, circumvents the tailor-made production of inefficient numerous prototypes, and thus reducing the development cost and reducing the time to market. So we can see that virtualization addresses and fulfills the needs of new and sophisticated strategic tools for innovation in the process industry generally, but why not in the food industry too, since all the advantages that we just discussed before are valid for the whole process industry and for the food industry particularly too. But what is the true big picture and what we are missing about this? So, is this run to innovation so necessary in the food sector? Now, if we look at the economic data, we see that for example, World Bank data in 2012 show food production index of 118 points, while a few years before it was 75.3, with the value of food and agriculture sector nearly about 5 trillion of US dollars, representing the 10% of the global GDP. So it seems that the food world goes very well. And if we compare also the turnover of food sector with respect to automotive and chemical industry and the value added, you can see that still the picture about the food world is absolutely positive. A little bit different picture comes when we look at the number of persons employed by the food industry. And you can see here that there's a very large number of personnel employed by the food industry with respect to the other sector. So now that I added value, it's the green column that you can see. If it is compared with the number of persons employed, well, the picture maybe is not that positive at all. And if we look at the overall research and development intensity for European, US, and Japanese companies, we can see that the food sector is the 13th with respect to other sectors which are invested much higher amount of money. You can see, for example, you can compare the intensity for research and development of the food sector with respect to pharmaceutical and biotechnologies, or aerospace and defense, software and computer services, and automotive. And actually, you can see that it seems that the interest to research and development is a little bit less urgent in food with respect to other sectors. Well, somebody can say that this is because the food sector is going very well, so why it has to put efforts in innovation? And if one thing that the worldwide highest one-year growth rate of net sales has been taken by the automotive sector, which was in the last years one of the sectors that mostly suffered for the economical crisis, well, that idea may be true. But actually, the sectors that are mostly benefiting of computational activities and virtualization are the same sectors that are applying more innovation in their products. I'm talking about, of course, aerospace and defense, again, automotive, and IT. So virtualization is strongly related to computing capabilities, and that's why in the past, when the computer power was low and thus computing cost was high, and the relative mathematical modeling activity was small and basically dedicated to these sectors, able to invest huge amount of money. But nowadays, the high computing power can be achieved with relatively low cost, and this has facilitated the growth of mathematical modeling activity, and the food industry can surely benefit of this. As I said, it's true for about food products that is needed to be reduced the time for developing. It's true about food processes that is needed a shorter time for design and for validate equipment and processes. And it's true that, for example, for household appliances, it's urgent to lower the development cost and to accelerate the time to market. So what was the purpose of using virtualization tools in other industrial sector is still true for the food industry. But please don't Google about food modeling or food virtualization, because what you can find is something slightly different from what I want to talk today. So I want to try to give a possible definition of the mathematical modeling activities in general and for food processing specifically. And I may say that for mathematical modeling, we can define the representation of a certain process or a certain product or a certain system made in a systematic way. So using the mathematical relationships, which often are complex system of PDEs, developed based on physical fundamentals. So I'm not saying that observation-based, so data fitting-based approaches cannot put in the category of virtual and modeling tools, but for sure they cannot be used in a generalized way, since they are often linked to the given experimental setup and equipment. So the observation-based approach provides a limited information about the inside of the mechanism of a certain process. So coming back to the definition, I have to say that the solution of this set of PDs lead to the process simulation in a computational way. So the virtualization is made by a process simulation that is based on computation. And this is exactly what is the goal of our cost action, combining mathematical methods and computer science to provide tools for the food industry. Then the mathematical modeling, the simulation are the first steps for feasibility studies, and they allow to prepare what is called the what-if scenario that can be investigated for further development, once again, of a product, of a process, or a system. Now, nothing is new. Everything has a solid basis and deep roots. And so the concept of virtualization starts with modeling and computer-aided techniques that back years ago were promoted by a number of illuminated scientists and professors and researchers around the world. So if there was a time that the solution of a one-dimensional PD was difficult and expensive thing, nowadays there are many possibilities. We can perform multi-physics modeling, mesh moving, multi-scale modeling, and so on. Now, if you search today the literature about the use of keywords food and virtualization, probably you will not get too much, because new terminology takes a bit to be familiar in a certain context, sometimes even to be accepted. But for example, when Professor Sagi edited this book about computer-aided techniques in food technology, not so many people were ready to read the word computer next to the word food. And during the year, a lot of work has been carried on by a number of research groups. And here I want to mention, for example, the great work done by Professor Hashim Datta from Cornell University. I'm just projecting a paper which I find very, very important, a pillar about the discussion of virtualization and modeling, appeared in 2008 on comprehensive use in food science and food safety. Now, just to give you some numbers and some tips about nice stories. First of all, what is considered the first paper about modeling and simulation is computer optimization of nutrient retention in thermal processing of conduction heated foods, appeared on Food Technology in 1969 and authored, among the others, by Professor Arthur Teixeira. Since then, a number of papers related to food modeling published per year has grown regularly. And you can see on Scopus that there are nearly 2,000 papers dealing with modeling, simulation, and virtualization in the food sector. Another very interesting datum is that almost 10% of these works are authored or co-authored by scientists affiliated to the food industry. So there is an interest of the food industry for this kind of work. And according to Dr. Watzke from Nestlé, who gave a fantastic presentation at the International Modeling and Simulation School in Food and Bioprocesses last year, among all papers about modeling, almost 1% is about food. And among all the papers related to food, almost 2% is about modeling. Now, keep on searching the literature, you may see that if you search sources having food in their title, there are more than 270 papers explicitly mentioning partial differential equations somewhere in the text. So going the direction I was talking before, to use the fundamental modeling as approach for simulating processes. And of those 270 plus papers, 240 plus papers appear in journals. So consolidated literature, not just conferences. And 210 plus papers mention the use of software, and among them, one can see that COMSOL, ANSYS, Abacus, and OpenFOAM are the more quoted commercial software used in this context. It's also interesting to see that this kind of keywords are becoming popular in the bio sector too. Now, if one focuses on food as a product or on food processing, sooner or later we'll understand that complexity is one of the keywords, because any food can be raw or processed. It's a complex system. It is heterogeneous by nature. It is multi-component. It's biochemically and microbiologically unstable, and during the processing, it's subjected to changes, both at structural and at appearance level. So any food process, traditional or novel, is quite complex too, in terms of mathematical description and description of its dynamics. So food processing is again multiphysics, because it comprises different disciplines and involves chemical, physical changes, also at different scale. This complexity needs to be taken in serious consideration. And so when we talk about the essential steps of mathematical modeling in food, whatever is what you are modeling, a food product, a food process, or a system used to process foods, one has to have a very clear that the complexity is there. And when there is complexity, it means that one has to find a way to reduce the complexity to get in a time shorter enough results which are meaningful. So first of all, there must be a problem definition. And in problem definition, a researcher must ask himself, what is under investigation? What is the phenomenon driving the given process? So the main one, what is the system configuration where the driving transport phenomenon is taking place? And what is the surrounding environment? Those are the four golden questions to set up the problem definition. Then, since we are applying a physics-based model that is based on theoretical laws governing the process, we should ask ourselves what are the balance we should write and why. And we have to ask ourselves if we know the constitutive equation of the food substrate, and we have to ask ourselves how we deal with the external environment. The third essential step is the definition of the process in initial status and boundary condition and the thermal physical properties. It is strictly connected to the first two steps. So we must suddenly understand if the study we are performing is a transient study or a steady state one. What is the initial state of the system, and what is the final state that we wish to attain? What are the boundary conditions? And boundary conditions, we don't forget, that are linking what is happening in the system with respect to the surrounding environment, and how to get the knowledge of properties appearing in the model. Properties are something that belong to that particular food substrate one is studying, is treating. So any modeling activity cannot be detached from experimental activities, especially about the measurement of the properties appearing in the model itself. Given the definition of initial and boundary condition, and given the definition of the properties appearing in a model, it's important finally to mathematically formulate the steps 2 and 3. So one must have clear the mathematical set to be solved, and then has to look at simplification of the process formulation when they are possible, in order to reduce the mathematical complexity, at least in a first attempt, because then there is time to make it more complex and extremely adherent to the reality. But in a first attempt, it's really, really important that one has to know how to reduce the mathematical complexity, of course, in a logical way. So know the mathematics, one has to look for the best solution strategy. Finally, we get to the computational solution strategy, and the first question one has to ask itself is, can I apply analytical techniques? So can I directly solve the PDEs where the various number of assumptions hold true? Or should I discretize the problem from a continuous formulation building up to an algorithm written, or by using a general purpose computational software? As we saw, there are many in the market, so there are many possibilities to use even complex system of PDEs. And then we got to the outcome, to the output of this modeling activity, where it is important to perform an intermediate analysis of the results, possibly using a common sense approach. So you have to find a way, you have to see where your solution is going, and you must have the sensitivity, and only studying and enriching your cultural baggage, you can get this sensitivity to understand if your intermediate results are going in the right direction. If not, you have to reformulate your problem and find for a better solution. And then you can finally process the data and verify the possible hypothesis put at the beginning of the work, and validate the model comparing the computational results with experimental data. After one has done this, as in its end, a virtual tool that can be practically used in his work. So this can be also summarized in this slide, where you see what is the logical path to be followed, also related to the steps I introduced before. So what can be designed with an approach like this? Can be designed a food product, a food process, a food processing system, and or a material or subsystem to be applied in a food process or a food processing system. I'm talking, for example, about a food product, about the fact that maybe you want to deliver a new microwavable meal, for example, a portion of a chicken breast and a portion of mashed potatoes, and you ask to yourself, how do I shape the food and its packaging in order to get the best cooking of this meal in a random domestic oven? So this can be done virtually by virtualizing the oven itself and the two products in the oven, and writing down the equation regulating the distribution of electromagnetic field in the microwave cavity and in the food substrate, and the heat transfer and the mass transfer coupled to this. And you can really play with the different design of the package and the food product itself to find out the best solution for it. Or, for example, if you have to design a food process and the need is to perform sensitivity analysis to the design of a new process for optimal curing of meat, again, you can, once you know the condition of which the process, the classical process operates, you can set up a model and explore just virtually, without spending too much money, what could be a change in this process operating conditions that can bring to an optimal design of your product, or an optimal design of your process. Or even in cases more complicated, and this is especially dedicated to my colleague Ferro Erdoglu from University of Ankara, who is listening to this webinar, there may be the need to design a new and better, for example, radio frequency assisted eating system. And yet, as you can see, it's possible even to build virtual tools where not just the basic physics describing the process can be set up, but also the actual movement of a product along a production line, like in the case I'm showing now in this slide. Another example is that by using a virtual tool, you can design, for example, a material or subsystem to be applied in food process or food processing system. And this, for example, is the case still in the field of radio frequency, of design a method and eventually an apparatus to improve the radio frequency heating uniformity in products. In this case was dry products, and simply by doing computational activity, it's possible to design a container in which this particularly dry food, can be hauled during the radio frequency operation, and to choose the material to make this container in order to help the electromagnetic field to deliver a more even heating to the system itself. Don't forget that in food processing, it is often, well, always required to deal with complexity to do simultaneous heat, mass, and momentum transfer. An example may be the coupled heat and mass transfer phenomena in multi-phase system, as in case of drying. You can also refer to frying, where beside to the heat transfer, it is important to take into account the moisture loss from the product, or for example, in case of frying, the transfer of oil inside the product itself. Again, a very interesting case is when this heat mass transfer and momentum transfer are coupled with other physics, such as, for example, displacement of an electromagnetic field. I thank Professor Jim Ling for sharing this slide with me, where you can see that at molecular level, water and ions can interact in a different way with the electromagnetic field as a function, for example, of the frequency of the field. You see from the left to the right, direct heating through ohmic heating, radio frequency heating, and microwave heating at the center, at the right hand side, as example of indirect heating. So you can see that increasing the complexity, you will have to increase also the mathematical correlation existing from a physics to another one. And again, in the case of radio frequency heating, one can recognize that there is a reason for coupling the different physics one with each other, not just because there is this power generated term, this QH EMW, which correlates the distribution of the electromagnetic field with the displacement then of the thermal field in certain products, but also must be taken into account that all the properties, in this case the electric and the thermophysical properties, can be function of the temperature, the moisture level, the ionic content, and the frequency of the field itself. So the interaction and the complexity often happens at different levels, but today there are enough strong tools to deal with this complexity in food products, food processes, and food production systems, so that there is no fear for the food sector to escape from the usage of virtual tools. And so I see that my time is running low, so few words about what modeling and virtualization will be. For me, they will still continue to be explored and used by researchers in the food world, but especially they will be a pillar of design in the food domain, especially for innovate existing products and processes, but also to invent new processes and invent new products, since the virtual environment is cheaper than any other experimental system, and allow to explore these what-if scenarios before putting the big money in hardware and stuff. Also, I believe that virtualization can be a very good tool to train new operators without blocking production operation. So imagine that you have virtualized a number of processes, and you can just train your operators in front of a computer. This is another big benefit that comes from virtualization activity. And I still see a lot of space about the use of these tools in manufacturing, because modeling will always be useful there. In innovation and healthy products, so it's easy to include design of devices for microencapsulation, for example. It's easy to use a virtual approach to test the bioavailability of a certain ingredient in a certain new products. And this goes in the direction of using also personalized nutrition as one of the domains in which virtualization may take place. And for sure, combining the predictive modeling with LCA tools, it's also usable in sustainability and for sure also in optimization. Of course, nothing is easy. Everything needs efforts, needs energy, needs investment, especially in human capital. But I like to give an appeal to the listener, and I want to say that when you start to do modeling, simulation, and virtualization activity, make it simple. There will be time enough to make it complex. And remember that nothing is so automatic and easy. And the key is a multidisciplinary approach. So even in modeling, it's not just a matter of mathematicians. It's not just a matter of computer specialists. It's not just a matter of food engineers. It's a matter to get together with other specialists and understand what is really important in your process, in your product, in your system to be mathematically described and mathematically solved. You know that we ran this year the second edition of the International Modeling and Simulation School for food and bioprocessing, and we are already working about the next year edition of the school. So thank you very much for listening, and be ready to join the Modeling and Simulation School in 2018. Thank you very much.